Hi, Chem students. I'm Mrs. Hessel, and welcome to your first lesson over atomic structure and nuclear chemistry. I'm starting today on page 4 in your notes. Please have out something to write with and a highlighter. The atom is the smallest particle of an element that retains the properties of that element. So on the left side, I have a picture of a sample of carbon. You can see the physical properties of that carbon. And then to the right, I have a picture of the atom of carbon, made up of protons, neutrons, and electrons. It's important that we understand these subatomic particles to get a better idea of the atom itself. So I'm going to compare and contrast these subatomic particles by charge, mass, and where they're found. So first of all, the electron. The electron has a charge of -1. Its mass is 9.11 times 10 to the -28 grams. It is actually the smallest subatomic particle, and it's found in the electron cloud. The proton. It has a charge of +1. Its mass is 1.67 times 10 to the -24th, and it's found in the nucleus. The neutron. It has no charge, hence neutron, neutral. Its mass is very similar to the mass of the proton, and they are both found in the nucleus. Protons versus electrons. If an electron weighed the same as a dime, a proton would weigh the same as a gallon of milk. Our little picture here shows that 2,000 electrons would equal the mass of about 1 proton. So the electron is about 2,000 times smaller than a proton. Although protons and electrons have very different masses, they have the same magnitude of charge, meaning the proton is +1 and the charge on the electron is -1. Where these different subatomic particles are found is important. The nucleus contains almost all of the atom's mass, but the electron cloud is responsible for almost all of the volume. Now this should make sense to you because it says the nucleus contains protons and neutrons. These are our heaviest subatomic particles. Now the electron cloud takes up a lot more space, but it contains these really lightweight electrons. If this positive particle below were the proton in a hydrogen atom, it would take a screen 1 mile across to display the electron's orbit. So what that means is this is a proton, so it's found in the nucleus, in the center of the atom. So the nearest electron would be half a mile this way or half a mile that way. It's just trying to give you an idea of how large this electron cloud is. The periodic table is organized in order of increasing atomic number. The atomic number is the whole number that's unique for each element on the periodic table. The atomic number defines the element. For example, if the atomic number is 6, the element is carbon. If the atomic number is not 6, the element is not carbon. I have a picture of the periodic table that we're going to use in class. This top number here is your atomic number, and this bottom number here is the atomic mass. So right now we're talking about the top number, the atomic number, and the periodic table increases by this atomic number. So you can see here I've got hydrogen, which is 1, helium 2, lithium 3, beryllium 4, boron 5, carbon 6, etc. So it increases by 1 going across the periodic table. And one thing it said in our notes is if the atomic number is 6, the element is carbon because the atomic number defines the element. So I know 6 is for carbon only. So what does the atomic number represent? It represents the number of protons in one atom of that element. It also represents the number of electrons in one atom of that element in a neutral atom. So protons and electrons are equal in a neutral atom only. Later we'll talk about ions where those numbers are not equal. I have some practice for you, and you can just use the white space at the bottom of your page to try this. Determine the number of protons and electrons in the following elements. Of course, you're going to need to look at a periodic table to figure this out. So go ahead and pause the video, look at a periodic table, and see if you can figure this out. Okay, welcome back. Sodium. So sodium has an atomic number of 11, which means that has 11 protons and 11 electrons. Magnesium has an atomic number of 12. So 12 electrons and 12 protons. And sulfur has an atomic number of 16, so 16 protons and 16 electrons. Again, electrons and protons will be equal in a neutral atom only. Isotopes and mass number. Isotopes are 2 or more forms of the same element that differ only in the number of neutrons. Okay, so this is where John Dalton had it all wrong. He thought that all atoms of one element are identical. This is not true. Elements have different isotopes. which mean that they only differ by the number of neutrons, which make their masses a little bit different. Okay, that's like saying twins, for example, weigh exactly the same. Well, they don't necessarily. One, if they spend a lot of time at the gym, may have more muscle than the other, and though their DNA is the same and they look the same, one may weigh more because of the amount of muscle it has. This is true with isotopes as well. So to figure out the mass number for a particular isotope, what you'll do is you'll add together the number of protons and neutrons. So protons plus neutrons equals the mass. To represent the mass and the atomic number of these isotopes, we use something called shorthand or isotope notation. On the right side here, this is an example of isotope notation for carbon-12. On top, we have the mass number, and on bottom, we have the atomic number. Now, the issue with this is kids often get confused what is written in the isotope notation versus what's on the periodic table. So I've got a picture here showing you the difference. Here's the part that can be confusing. The atomic number on the periodic table is the top number, but the atomic number for isotope notation is the bottom number. Please don't get these confused. On the bottom of the periodic table, we've got average atomic mass, but on the top of isotope notation, we've got mass number. Again, remember, this is protons plus neutrons. Here I've got examples of isotope notation using 3 carbon isotopes. There's 2 ways we can show isotope notation. I can write out the name dash the mass number, so we've got carbon-12, carbon-13, and carbon-14, or I can use that other form of isotope notation that I showed you before, where the top number is the mass and the bottom number is the atomic number. Remember, the atomic number represents the number of protons. In a neutral atom, this is equal to the number of electrons. So looking at our 3 different isotopes of carbon, let's figure out more detail about it. What are the subatomic particles? Every atom of carbon has to have 6 protons. Remember, that's its atomic number. It defines the element. However, because these are different isotopes, their neutrons are going to differ. Since protons plus neutrons are supposed to give us the mass number, we can just subtract to figure out the number of neutrons. So 12 minus 6 gives us 6 neutrons. 13 minus 6 gives us 7 neutrons. And 14 minus 6 gives us 8 neutrons. So as you can see in our 3 different isotopes of carbon, the only thing that makes it different are the number of neutrons in the atom. I am going to want you to be able to calculate the number of electrons, protons, neutrons, and the mass number for a particular element. So we've come up with an acronym that makes it really easy for you to do this. It's APEMAN. So let me tell you what APEMAN means. So APE is the first one. The atomic number equals the protons, which equal the number of electrons. And then MAN, we've got the mass number minus the atomic number equals the number of neutrons. So basically, the top number minus the bottom number in our isotope notation will give you the number of neutrons. So 14 minus 6 is 8, which would give us 8 neutrons for this particular atom. Here's a table showing our 3 different isotopes of carbon. How many protons, electrons, and neutrons are in each isotope of carbon below? Let's use APEMAN to help us out. So we know A equals P equals E, which means the atomic number equals the number of protons and electrons. So we can just look up carbon on our periodic table, and we can see that its atomic number is 6. So I know that every isotope of carbon must have 6 protons and 6 electrons. Next, I'm going to figure out how many neutrons, and that's when I can use MAN. M minus A equals N. So the mass number is written here. We're going to subtract the atomic number, which is the same as the number of protons, and we'll get the number of neutrons. So 12 minus 6 gives us 6. 13 minus 6 gives us 7. And 14 minus 6 gives us 8. APEMAN, it makes our lives so much easier when trying to figure out the number of protons, electrons, and neutrons in an atom. Okay, I hope you enjoyed this lesson today. Just to make sure you were paying attention, we reviewed subatomic particles, their location, size, and charge. We talked about the atomic number and that it defines the element. And lastly, we talked about different isotopes of a particular atom, and that John Dalton was incorrect when he said all atoms of one element were identical. That's not true. We've got different isotopes that vary in the number of neutrons. This concludes today's lesson. I hope you understood everything we talked about. If not, please feel free to ask your teacher in class. Have a good day.